KOMVEE Software Systems is a limited liability partnership firm incorporated on 11 December 2014. We are a young engineers team to address the most important issue of water treatment plant process design and sewage water treatment plant process design solutions for educational institutes in India, especially in the field of environmental engineering for DE and BE students of civil engineering. In STP-PD, we shall see how sewage from the city is treated and safely discharged. Accordingly, we shall provide the entire process design stepwise, starting from the screen chamber till the digester beds to develop the plant. The steps involved in this are screen chamber, grid chamber, skimming tank, primary settling tank, aeration tank, trickling filter, secondary settling tank, digester unit, and finally the digester beds. Now we shall see how STP-PD works. Let us consider the first module, that is screen chamber. Each module has a specific layout, that is, we have an input window for entering the required variables to be considered for calculation. We shall now proceed to enter the values one by one. The first field is for the project title. Next is the flow rate. Then the peaking factor. Next, the BOD. After that, the total suspended solids. Then the temperature. After this, the inclinations of bars. Then the size of bars. After this, we have the length, the width, the depth, the clear spacing between the bars, then the velocity of flow normal to the screen, then the number of bars, and finally the freeboard, after which we have Manning's coefficient. Now that we have entered all the required fields, we shall proceed to calculate the output. As we can see now, the output is displayed before us. Over here, we have the average rate of flow, then Q, then the net submerged area of the screen, the gross submerged area of the screen, the velocity of flow in the screen chamber, the number of openings, the gross width of the screen chamber, the liquid depth, total depth of the channel, hydraulic mean depth, and the slope of the channel bed. We can also proceed to see the diagram for the screen chamber. Based on our required inputs, we can see that the diagram for the screen chamber has been generated. We can also export the DXF and then save the record accordingly. Now we shall proceed to consider the module for grid chamber. Here, the first field is specific gravity of particles. Next is the acceleration due to gravity. After this is the diameter of the smallest grid particle. Then the kinematic viscosity. After this, the depth of the grid chamber. Now we have specific values for W1, W2, W3, W4 and W5. Now that all the values have been entered, we shall now proceed to calculate the output. we can see now, our output has been generated. It reads out as follows. We have our average flow rate and the setting viscosity and Reynolds number, the bi-transition law, the viscosity, Re, the drag coefficient, the displacement velocity, the area of grid chamber, the length of the grid chamber, the width of the grid chamber, the peaking factor, the width, and based on the W inputs, we have our H1, H2, H3, H4, and H5. We can also generate a diagram now. Based on our inputs, the diagram for the grid chamber is accordingly generated. We shall now proceed, save the record, and proceed to the next module. The next module that we shall see is the skimming tank. Over here, we have only two input fields, the first of which is the depth of the tank and the rising velocity of the greasy material. Now that our inputs have been fed, we shall proceed with calculate the output and generate the diagram. In our output, we have the flow rate, the rising velocity of the grease material, the surface area of the skimming tank, and the diameter of the tank. Also, we can see that our diagram has now been generated based on our inputs. We can now proceed to save the record and proceed to the next module. We shall now consider the model for the primary cycling tank. The inputs are divided into three stages. We shall first consider the design of the primary settling tank. Our first input field here is the surface overflow rate, then the weir overflow rate. After this, the side water depth, the number of tanks, the bed slope, and W. After this, we shall consider inputs for the design of the sludge hopper. Our first input is for the percentage of solids removed by the grid chamber. After this, the solids in clarifier. Then, the percentage of solids removed by the clarifier. Our total percentage of solids A and percentage B. Next, we have specific gravity of volatile solids. Then, for fixed solids. Then, the percentage of solids dried in the clarifier. Then we have SW and PS. Next is the frequency of cleaning of the sludge hopper. After this, the frequency of cleaning of the sludge hopper in terms of days. After this, we have the angles to consider. Finally, we enter the input for RB2. Now we shall proceed for the inputs for the design of the collection channel. Our first input here is the velocity of the flow in the channel. Next, the width of the channel. Now that all our inputs have been entered, we shall proceed to calculate the outputs. Our outputs have now been generated. As we can see, for the design of the primary settling tank, our outputs are for the flow rate, then the ratio, after which we have the area of the tank, the area of each tank, the diameter of the tank, the flow through each tank, check for WOR, the volume of the tank, the detention time, the depth due to the slope at the center, and the total depth. Next, the output for the design of the sludge hopper. The total suspended solids, the dry solids, the suspended solids, SS, specific gravity of sludge, volume of sludge, volume of hopper, the angle, angle for tangent, volume, and finally, at the end, we have the height of the hop. For the output for design of collection channel, we have the area of the channel, the depth of the channel, the freeboard, total depth, packet perimeter, hydraulic mean radius, Manning's coefficient, slope of the channel bed, and the slope. We shall now proceed to generate the diagram for the primary settling tank. As we can now see, based on our inputs, the primary settling tank diagram has been generated. We can now proceed to save our record and proceed to the next module. The next module we are about to consider is for the trickling filter. Over here, the inputs are divided into 5 stages, the first of which is for the design of the trickling filter. Our first input field over here is effluent BOD, then the recirculation ratio, then the depth of the trickling filter, and finally the number of units. The next input stage we shall consider is for the design of the central pipe and distributary system. So, our first input field is for the velocity of flow. Next, the provide sections. And finally, the joint length. Now that we have entered the inputs, we shall consider the next input stage. Our next input stage to be considered is for the design of the orifice. Here we have the drag coefficient, the depth of the orifice, the diameter of the orifice. Now we have the proportionate area of sections in percentages. Accordingly, we shall enter the percentages of first section, second section, and third section. After this, the next input stage is for the design of the under drainage system. So we have the spacing of the under drain and the velocity of flow. Our final input stage is for the design of the collecting channel. Here, the input to be considered is the width of the channel. Now, we should proceed to calculate the output. Now that our output has been calculated, we can proceed to examine it. For the design of the trickling filter, we have the flow rate, the influent BOD, the overall efficiency, the upright BOD, the area of trickling filter, the diameter of the pipe, the hydraulic loading rate, and the organic loading. Next, we have the design of the central pipe and distributary system outputs. Here we have the flow after entering in the central pipe, then the peaking factor, then the flow of the central pipe, the area, diameter of the pipe, the average velocity, then the diameter of the TF, then the length of each arm, then the length of all the 3 sections, the area of the sections, the proportionate area for each section, discharge per section, the area of the sections, and finally the diameter of the sections. Then for the design of the orifice, we have the area of the orifice, the discharge to the orifice, the number of orifices required for each arm, the number of orifices in each section, the spacing of the orifices, and the next output stage over here is the design of the under drainage system. Here we have the diameter of the TF, the number of laterals, the average slope of filter, the discharge to each channel, the area of each lateral, checking for average velocity, and the radius of lateral. Our final output stage is the design of the collecting channel. Here we have the area and depth of the channel, Manning's coefficient, hydraulic mean radius, slope of channel, and volume. Now we should proceed to generate a diagram for the trickling filter. Here we have the required diagram based on our inputs. We can now save the record and proceed to the next module for the secondary settling tank. Our next module is for the aeration tank. Over here, the first input field we shall consider is for the percentage recirculation. Next, the aeration period. And finally, the depth of the tank. Based on these inputs, we shall now calculate our output. Now that we have calculated our output, we can proceed to see it. We have our flow rate and the percentage recirculation, the volume of returned sludge, the capacity of the tank, the area of the tank, and the diameter of the tank. Now that we click on the diagram tab, we shall see that the aeration tank diagram has been generated based on the previous inputs. We can now proceed to save the record and go to the next module. We are now going to consider the module for the secondary settling tank. Here, we shall enter the input for the depth of the clarifier. Next, for the percentage of solids removed by the trickling filter. Then, the production of solids in the trickling filter. And finally, the percentage of dry solids. Now that our inputs have been entered, we shall proceed to calculate the output. Our outputs have now been generated. We can see them as follows: the flow rate, the flow to the secondary settling tank, the surface overflow rate, the recirculation ratio, the total flow through the clarifier, the area of the clarifier, the volume of the clarifier, the diameter of the clarifier, V, H and their ratio, the total depth at the center of the clarifier, and finally the detention time. Also, for the design of the sludge hopper, we have the specific gravity of sludge, the volume of sludge, dry solids, STP, and finally the volume of sludge produced in the secondary settling tank. We can now generate the diagram as per the inputs entered. And as we can see, the required diagram has been generated. We can now proceed to save the record and proceed to the next module. We shall now consider the module for the digester unit. Our first input field over here is the time required for digestion. And finally, the height of the digester. Now we shall proceed to calculate the output. Our outputs are as follows: the volume of sludge from the TST, the volume of sludge from the SST, the volume of fresh sludge, the volume of the digester sludge, the volume of the digester, the area of the digester, diameter of the digester tank, the dry solids in the TST, the dry solids in the SST, total volume of sludge, the volatile solids destroyed, the VSD, the quantity of total gas produced during digestion, and the quantity of methane gas produced during digestion. Now, we can generate the diagram for the digester unit. As we can see, the required diagram has been generated. We should now proceed to save the record and proceed to the next module. The final module that we are considering is for the sludge drying beds. Our first input feed here is the depth of the sludge application. Next, the length of the drying bed. And finally, the frequency of sludge removal. Now we should proceed to calculate the output. Our output is as follows: the volume of the sludge digester, the area of the sludge drying bed, the width of the drying bed, and the number of sludge drying beds. Now that we click on the diagram tab, we can see that according to our inputs, the required diagram for the sludge drying beds has been generated. We shall now proceed to save the record. Now that we have seen the working of all the modules, we shall see the working of the Super Run tab. Here, we simply click on the System option and select the tab for Super Run. In the new window, we shall now click on the Browse button. Over here, we shall select the required file to be inputted. The file should have a WTS extension. Now that we can see that our file has been selected, we shall select the option for Run. Now we can see that the output for the complete system has been generated. Right from the screen chamber module all the way up till the sludge drying beds. We can slowly scroll down through all the modules and examine our outputs. Now that we can see that our output has been generated, we can now decide what options to select. If we decide we want to edit any particular information in the input feeds, we can do so and accordingly save the changes later. In order to save the changes, we shall scroll right down to the bottom of the document. Over here, we have three options: export to Word, save record, and save to file. The first of these options that we shall be exploring is save record. For example, let us consider the option for sludge drying beds. If we decide to change 0.3 to, let's say, 0.4, if we select the option for save record, now that this has been done, we shall scroll down to the bottom. We can see now that the option previously where we had inputted 0.3 has now been changed to 0.4, which means that the changes have been saved in the very same file. The option for save to file means that if we decide to select this option, an exact duplicate copy of the current file will be created. Later on, we can input that file into the system and make any changes that we feel are necessary. The final option we shall explore is export to Word. On selecting the export to Word option, we can see that a pop-up window comes up asking us whether we wish to open or save the document. This basically means that the outputs that we have seen are saved in the MS Word format. For now, we shall close this window and explore two connected options at the top of the screen. These options are Complete Report and Report. As we can see, the button for Complete Report has been selected. The way they're connected to the Word tab is that if we select the button for Complete Report, the contents of all the modules will be copied into our Word document. That is, all the way from screen chamber all the way up to sludge drying beds. In another case, if we decide to select the button for Report, we can see that this button is related to screen chamber. After selecting this button, if we select the option for Export to Word, only the contents for the screen chamber module, that is the input, the output and the diagram, will be copied to the Word document. This is how these particular buttons work. The tutorial is now complete. Hope you found it useful. Thank you.